Today's speaker is myself, and I will be talking about dynamic games played over event trees with coupling constraint. The seminar today is a bit different from usual in the sense that one large part of it is a tutorial about this class of games. So specifically, I will start by introducing DGPETs, and after that, I will deal with the case where we have coupling constraints. I will illustrate the theory with a paper that will be published soon, a joint work with Elena Parina and Stefan Rauchek, and after I will conclude by some remark. Please interrupt me whenever you want if you have questions, and do not use the chat because I cannot handle it. Okay. I am interested, in fact, by problems that have the following characteristics or features. One is that you have a competition between few agents, and this is the famous expression about competition among the few. We have accumulation process that are involved in the game, and we have some uncertainties about the parameter values. The first characteristic points toward game theory as a framework to deal with this kind of problems. We have strategic interactions. Here you have some examples of accumulation processes. For instance, knowledge, when you invest in research and development, production capacity, you may increase or decrease your capacity, and pollution stock each time you produce something. I guess when we have a problem that is evolving over time, it makes a lot of sense to consider that we do not know beforehand the true parameter values, at least not all of them, and uncertainty becomes part of what must be done. So if you have these three characteristics, stochastic dynamic games are a natural approach to deal with these problems. The case I'm going to deal with is the case where stochasticity takes the form of an uncontrolled event tree. What I mean by that is that decision makers are given a tree that is describing the evolution of uncertainty about some of the parameter values. And contrary to the classical case of stochastic games, here the transition from one node to another is not controlled by players' actions. Just to give you... Sorry? Okay. Just to give you an example that you can keep in mind while following the talk, you might be interested for having an idea about the inflation rate next year, and we are at this period, so you may consult the Bank of Canada or any other institution and look at the different scenarios that they are considering for the inflation rate next year. So it can be this one, that one, etc. And what you have are probability transitions between one node to another. Okay. So again, here, this event tree is given and cannot be controlled. So to define a game played over event trees, I need to do two things. One is to define the elements that are necessary to define the event tree, and also the element of the game themselves. So let me start by the event tree. What I'm considering here is the case where I have capital T period. So for instance, here we have a case where we have 1, 2, 3, 4 periods. And we have a stochastic process, xit, that is described by this event tree. As usual, when you want to describe an event tree, you need to specify the root node, and this is called N0. And after that, at any instant of time, for instance, at t equal 1, you have a set of nodes that are there. I will be denoting by NT minus a node that is a predecessor to node NT, and this is a unique predecessor. For instance, if I am at this node, this one is the node NT minus of this particular one. I will be denoting by new a successor of node NT. For instance, this node is a successor of that one. And NT plus is the set of all direct successors of node NT. So if I am at this node NT, these are the direct successor of this one. And NT plus plus is the set of all nodes having NT as their root node. So in particular, N0 plus plus describe the entire event tree. Okay, so this notation is pretty straightforward. Now, as in stochastic programming, we refer to a scenario as a path emanating from initial node or root node to any terminal node. So this would be called a scenario. The probabilities of all scenarios is equal to 1. And we can use this notation to mention what are the nodes that are encountered on the unique sample path emanating from N0 to go to NT. So for instance, this is one particular path here. One element that I would like to highlight here is that any node is representing the history of the Xi process. For instance, if you are at this particular node, you can go back to the initial or to the root node. And from this perspective, you can say that being at a particular node gives you the information about the history of the stochastic process up to this particular node. In terms of probabilities, pi nt will be denoting the probability of passing through one particular node nt. Of course, the probability of n naught is equal to 1, and probability of n capital T, which is a terminal node, is probability of the single scenario that terminates in this terminal node. For any node nt, of course, the probability of being at this node is the sum of the probabilities of the successors. And after that, we have this notation. I mean, I'm putting it here for being complete, but it will not show up that much in the rest of the talk. So let me skip it. So with that, I completed the description of the event tree on which the game will take place. Now I would like to say, to define the game itself. So this is a dynamic game. So we have a set of players. I have m players here. And at each node nt, we have some control variables. So for player I, we have these control variables ui and t that belong to the set of admissible control. Okay, so capital ui and t is the set of admissible controls for player I when we are at node nt. U superscript I in bold is the product of the sets of decision variables of I belonging to M, and U and T is the joint decision set at node NT. Okay, again here the notation is pretty straightforward. We have state equations. So what we have here is the state at node NT depends on the state at the predecessor node and the vector of controls that have been implemented by the players at node NT minus. Okay. The payoff functional are given by the instantaneous payoff. So this is the payoff that player I will collect at node NT, given that the state is given by X and T, and the players are implementing this control vector. Pi nt is the probability of being at this particular node. So we are taking the sum over all nodes and discounting it at discount factor rho. And this is what is happening at a terminal node. What we are assuming here is that at a terminal node, there is no decisions that are made. So what the players are collecting is a payoff that depends on the node itself and the state variable that the state value at NT. So I define the set of players, control state equations, and payoff. I still need to define the information structure that I will be dealing with. It's well known that when you have a dynamic game, the results will depend on the information structure that one adopts. Here, the information structure that we have is called S-adapted open loop information structure. From where this S is coming, it's simply because it refers to the idea of sample of the stochastic process. So for instance, when you are at this node and looking at inflation rate next year, of course, inflation rate is a continuous variable, but what we are doing is sampling this continuous variable by considering number of values. The game is played in open loop in the sense that decisions are not adapted to the state of the system. However, there is a big difference between the usual open loop information structure and the S-adapted open loop information structure. Here, what we are going to have is a situation where the decision variables are indexed over the set of nodes, meaning what? For instance, if I am at this particular period, the decision that will be taken at each one of these nodes is not the same as at other nodes. So meaning that if you are looking at investment here, you may invest at this node very differently from what you will do at this one. Whereas in an open loop information structure, because you would be solving the problem of maximizing an expectation, the same decision will be implemented at all nodes belonging to the same period. So this is crucial to understand in terms of difference between the S-adapted open loop information structure and the open loop information structure. Now, we can deal with the case of S-adapted feedback. This was done with Vishwa Reddy in a paper in Automatica in 2019. So here what you need to do is, of course, to proceed backward and for each sample, for each pass to solve the problem adopting formalism of dynamic programming. However, here there is one subtle thing that you need to take into account, that, for instance, the state at this particular node is common to all nodes that are coming later. So when you are solving along this path or solving along this path, you have to account for this particular feature. So what is a strategy? As usual, a strategy is a function that depends on the information that is available to the players. And this is what is available at any one of these nodes. Some comments on the control sets. So when we are at node NT, the control set is given, as I mentioned before, by UI NT. And this control set can have different forms. One possibility is to have this control set independent of the state and nodes, meaning you have a control set that is invariant over all these nodes. One possibility that it's a bit more complicated is to have the control set being dependent on the position of the game, meaning that this UI NT varies with the node and varies also with the state at this particular node. In this case, what you will have is a constraint saying that UI and T, the decision taken by player I at this particular node, must belong to this feasibility set, and this feasibility set depends on the node, on the state where we are. The more complicated situation is when we have coupled sets, and this is what I'm going to deal with later on. So this is an example where you have coupling. For instance, at node NT, these are the decisions made by the M players, and all of them are facing a constraint that says that this function applied to this one to this vector of decisions should be larger or equal to 0. Okay, so meaning here that when a player is choosing his or her control, he or she must take into account the fact that by doing this or that, this condition or constraint may be violated, and something has to be coordinated here. I will assume throughout the presentation that the state set is invariant over nodes and time periods. This is essentially to simplify the presentation. Now, the terminal time can be given, as I'm going to assume here, but in fact, the whole theory that has been developed in this area can be extended to the case where the terminal time is random. If you are interested, there is a paper, if I remember well, in Jota with Elena Parellina dealing with the case where we have random time. So in fact, in this case, you have to add at each node the probability that the game may end for force majeure case or whatever you want to capture. Okay, so now given the elements of the game, one step that is useful to do is to represent the game in normal form. The reason why we would like to do this is that if we can represent a game in normal form, we can use the machinery of existence and the uniqueness of equilibrium that has been developed for normal form games. So to do it here, what we should note is that the state X is the unique solution that is obtained by implementing U, which is a vector of control, emanating from X0. Once you have done this, now the payoff function that I defined as a function of the state and control now can be written only as function of control or the strategies. Simply by doing this trick, you will change X by, this is the right-hand side of the dynamic for any node and a terminal node and T. So now your payoff function is written simply as function of the strategy and the initial state. So with U defined as the profile of the M players as adapted open loop strategies, we have a game fully defined in normal form. To define a normal form, I guess everyone knows that you need a set of players, which we have here, strategies and payoff function. Okay. Now, by doing this, as I said, we can use the classical or standard machinery for defining Nash equilibrium and its existence and uniqueness. So an S-adapted Nash equilibrium is an admissible S-adapted strategy you start such that for every player I in M, you have the following inequality. Inequalities hold true, and you recognize here the classical definition of a Nash equilibrium. Now, in terms of existence, you have several theorems that give you the conditions for existence of a Nash equilibrium. We are using here Rosen theorem, which says that if the reward functions f phi I for all players are concave in the control and the previous one for any node, and the terminal payoff is concave in UN minus for any terminal node, and if the set of S-adapted strategies is compact, then there exists a S-adapted Nash equilibrium. I guess this is the kind of theorem that we teach in any 101 game theory course. Now, for uniqueness, the first step is to introduce these tilde vectors, UI at n minus t and nt, to write down the Jacobian matrices. And after that, we can use again a theorem given in Rosen, saying that if these matrices are negative definite for all nodes, then the S-adapted Nash equilibrium is unique. So let me wrap up here that a game played over event trees, can be we can define the equilibrium in terms of S-adapted strategies. But since we can write the game in normal form, we can use the usual machinery for existence and uniqueness. Now, this being said, if we want to compute the equilibrium, we need to proceed as usual with a dynamic game to write the formalism in multi-stage game and to state a maximum principle. So what do we have here? Start by defining player I's Hamiltonian. So this Hamiltonian will depend on the node, on the state, on the control, and of course we have a vector of or collection of adjoint variables. And this is the Hamiltonian. So you have the current or the instantaneous payoff at node NT plus rho, which is the discount factor. And here you have the summation over the nodes that belong to the successor set of this particular node. Here you have the right-hand side of the dynamics. This is the probability of each one of these nodes. And you have this vector. So this vector is different from the usual multi-stage game in the sense that it is an average sensitivity vector that we are considering here, where this pi nu nt is simply pi nu divided by nt, which gives you the transition probability from one node nt to a successor. Now, once the game is defined in multi-stage and we have the Hamiltonian, now we can state a maximum principle. So if U star is an S-adapted Nash equilibrium generating the state trajectory X star over the event tree, then for any player I, there exists a co-state trajectory lambda I such that the following conditions hold. And you recognize here the optimality condition and also the conditions governing the evolution of the co-state variable. And of course, this must hold at U nu equal to U nu star and x nu equal to x star nu. Now, given these conditions, you can apply them to the problem you are dealing with and determine the equilibrium strategies. Okay, so now I want to enter this coupling constraints. Sorry, a second. So as I mentioned earlier, we have coupling constraints of the following form. At any node NT, what all players are doing is coupled in the sense that they must collectively satisfy a constraint like this one. So here, each player's strategy space may depend on other players' strategies. And this is the case that it's typically not covered in a game theory course because it leads to some complications. So here again, I'm calling open this famous paper by Rosen in Econometrica 65 to deal with this kind of situation. So what Rosen showed in the case of concave games is that to deal with this kind of situation, what we need to do is first to solve a weighted sum of players' objectives. Now you have n players, give to each player a weight, so Ri to player I, solve the joint problem appending a multiplier mu to each one of these coupling constraints. So you obtain the values of these Lagrange multipliers depending on the number of constraints that you have. And after that, decentralize the situation by determining a Nash equilibrium where player J is affecting or appending this multiplier, which is the common multiplier that was obtained in the joint optimization, divided by Rj, where Rj is the player that is given to player J. So here we talk about Rosen equilibrium, and sometimes it's referred to it normalized equilibrium. Some literature is calling it also generalized Nash equilibrium. I think it's abuse of language here. I prefer either Rosen equilibrium or normalized equilibrium. So the theory regarding normalized equilibrium in dynamic games has been developed 25 years ago, more or less. So in the case of deterministic differential games, you have papers by Dean Carson and Alain Horry. They gave all nice conditions and very nice characterizations. And I joined both of them to write this chapter in the handbook of dynamic games, explaining maybe it a little bit more pedagogically how this coupling constraints work in the context of deterministic differential game. Now, if I want to translate how it works in the context of dynamic game, in the context of dynamic game played over an event tree, so I will have the following definition. The S-adapted Nash equilibrium is normalized if the Lagrange multiplier, so mu is any of the coming nodes, are collinear with a common vector, mu not mu for any player I, such that we have this condition. So as I said before, it means that we have determined the common vector of Lagrange multipliers, and this is after that decentralized to the players by having this multiplier taken the common one divided by Ri. Now, given this formalism, we can state a maximum principle for this class of games, and this is what has been done by Elnaz Kanani Kushesvihani in her thesis. So in a Jota paper, she showed that under the following assumptions, meaning that the right-hand side of the dynamics and running payoff are continuously differentiable in the state and control. The terminal payoff is continuously differentiable in the state. And if the control set UI and T is defined by inequalities, mappings RLI into RCR are given differential mappings. So under these assumptions, you can state a maximum principle. I will not state it here because it takes, I think, 5 slides, even by cutting short some pieces, but I will illustrate how it works later on in the example. By now, you should ask yourself, okay, everything is going nicely, but from where this vector of weights is coming? If you ask a mathematician this question, he or she will answer you, who cares? What I'm interested in is to do the following: give me a vector of weights, and I can state the conditions for existence and uniqueness of equilibrium, and eventually extending it to dynamic setting where we can have a maximum principle. Now, interestingly, there is a large literature in resource, energy, and environmental economics where the story goes as follows. You have a regulator in charge of enforcing the joint constraint. And so the regulator is solving the joint optimization problem, getting the joint Lagrange multiplier, and after that telling the players what is their multiplier in this sense. So why the regulator is doing this? But because the regulator can enforce this, and the choice of the weights can then be determined, for instance, by which player is polluting more, or which player is easier for him or her to reduce pollution, so on and so forth. So here the choice of the vector will depend on the story that you are telling. And this literature is almost now 30 years old. You have a long series of papers, as I said, in energy and environmental economics. I don't know if Mabel is here. She does not seem to be attending.
Oui, I am here.
You are
Yes.
here. So
Yeah.
Hi, Mabel.
Hi.
So with Mabel, we were for a long time intrigued by this vector, and we said, let us try to have a particular interpretation of this vector. So what we showed in this, what I believe a nice paper, is that in fact you can define the vector R such that you can reach a Pareto solution. And anytime you can do it, this is a very nice solution because it means that this vector has a very clear definition. What we are after is to reach the Pareto solution. We tried hard to extend our trick to a dynamic game. It does not work. In fact, why? Because if you want to have a fixed vector over time, it's impossible to do. However, if you want to change at each instant of time the vector, you can achieve it. But since what we did is in differential games, I think it was very hard to swallow the idea that at each millisecond, the weights are changing. But maybe in a discrete time where periods can be sufficiently long, maybe it's worth it to revisit this problem. So, Mabel, maybe this could be our next paper. So, let me now illustrate the theory with an example, but before moving to the example, any questions or comments? So two possibilities here, either everything is clear or nothing is clear. Let me assume that everything is clear and move forward. Okay, so the story I'm going to tell here is somehow inspired by what we lived during the pandemics, namely that we witnessed some shortages in some markets and in some supply chains were perturbed. So the story goes as follows. We have a set of sellers, retailers, buying from a common manufacturer a product. And we have the following environment. It is a competitive environment, meaning that these retailers are competing in a certain market and their profits are interdependent. And since inventories are playing an important role here, there is no way of dealing with this kind of competition with a static game. So what we are assuming is a dynamic environment. And we have one stochastic feature in the model, namely that the total supply of the manufacturer is uncertain. Okay, so these are the main elements. I hope that by now you are convinced that when you have a setup like this one, a dynamic game played over an event tree can be the right model. So here what we are going to have is at each node, each retailer will be choosing the quantity to put on the market and how much to order from the manufacturer. So these are the strategic variables. So what are the research questions that we are after here? One is what are the Rosen quantities and order equilibrium values in this game? And from an economic perspective, it is interesting to study how a possible disruption of supply can affect retailer strategies. And of course, in a model like this one, it's always of interest to do some sensitivity analysis by looking at what would be the impact of varying some of the parameter values. So the model, we have a set of retailers, M retailers. Here we are going to assume that the manufacturer is non-strategic. So the manufacturer is simply posting a wholesale price W. Obviously, a nice paper for a PhD student is to extend what we are doing here to a supply chain by having the W a decision variable. So you have not only horizontal interaction, but also vertical interaction. We have a set of capital T periods, and the total supply by the manufacturer at any node NT, which is denoted by SNT, is uncertain. In fact, we can even deal with, we want to deal, in fact, with even the case where we have total disruption in the supply chain, meaning that the manufacturer is not able at all to produce, so SNT would be equal to 0. This is a typical case that can occur if you have a labor dispute, a lockdown, or a transportation mean is not available, etc. And we are going to represent the uncertainty by an event tree. So formally, the decision variables are going to be denoted by Qj for the quantity or sales at node NT, by Oj the order quantity. At the last period, there is no decision that is made, so the orders are equal identically to 0. We are going to assume for illustration purpose that the inverse demand function is given by linear one. So it's equal to alpha minus beta QNT, where QNT is the total sales by the M players at node NT. The state variable here is the inventory that is available to player J at node NT, and the state dynamics are as follows. So the inventory that is available at NT is the inventory that was available at NT minus, so at the predecessor node, plus the orders that have been made at the predecessor node, plus the sorry, it should be minus here, the sales at this particular node, okay? So the inventory at node NT is inventory at predecessor plus orders minus sales. And of course, you have to specify the inventory at initial node. So what kind of constraints we have here at any node? Sales by player J cannot exceed inventories. So it means that at initial node, it cannot exceed the initial inventory. At any node NT, the sales cannot exceed the inventory that was available at NT minus plus the order at NT minus. We have also another constraint, which is the constraint that the total orders from all players to the manufacturer cannot exceed the production capacity of the manufacturer. So here what I want to highlight is that we have some constraints that are specific to the player, and we have this one, which is a coupling constraint. Now, of course, player J may want to get the whole supply that is available at the manufacturer depot, but this player has to take into account that the fact that also other retailers are interested in fulfilling their orders. So the payoff function of player J is, this is the price minus the wholesale price multiplied by the quantity minus the holding cost of the inventory, at all this at node NT multiplied by the probability of being at this node, summing all probabilities, discounting at discount factor rho, and this is what is happening at the last nodes. So here you have sales, but you don't have orders, and this is the salvage value, meaning the value that you can get from having an inventory at this terminal node. So for the sake of writing the results, let me rewrite the constraint. So this is the constraint of selling something that is less than what you have in your inventories. So meaning inventories plus order minus sales should be non-negative at all nodes. And this is the coupling constraint, meaning that at node NT, this is the available supply minus all deliveries cannot be negative. And observe that this function and this one are linear. Now, this is the kind of slide that I tell my students to never show in a presentation because it's terrible, but still I need it here. And to understand it, please follow the colors. So I'm writing here the Lagrangian that corresponds to the maximization of the joint payoff. You remember to define a Rosen equilibrium, I have to maximize the sum over the weights multiplied by the payoff of the players. So what do I have here? Everything that is in blue are payoff. So for instance, this is the payoff at node 0. This is the payoff at any node NT. And of course, I have to sum over the nodes and to discount. What is in green? This part is the right-hand side of the dynamics multiplied by the co-state variable. And in this, I don't know the name, maybe it's magenta color. So this is the constraint saying that what you can sell cannot exceed what you have in the inventory multiplied by the Lagrange multiplier. So you have it at all nodes. And this one that is of interest to us, which says that this is the coupling constraint. And what the regulator here is appending a Lagrange multiplier to this coupling constraint at all nodes. So here it's at node N0, and this is at any node NT. And of course, this is under the sum. So for someone, the regulator or the manufacturer or whoever is in charge of solving this problem, solving it will give this, in particular, this multiplier, and after that, we can decentralize the solution to the players. So we have here a theorem stating what is the normalized equilibrium. So Q star and O star is a solution to the joint optimization problem, and we have the optimal state trajectory. So if the strategy and state sets are have empty interiors, now we can show that there exist multipliers such that the following conditions hold. You will have here the optimality conditions, co-state equations, and of course, the complementarity slackness conditions. It does not help really to write them. It will take a number of slides, but I think everyone is getting the idea here. Now, once I get this, as promised, I want to decentralize the solution, meaning that I want to have the solution satisfying the joint constraint through the definition of players multipliers that must be appended to the constraint that they are facing at any node NT, and this is by the introduction of these multipliers. So you can think of this term as a penalty term. So what would be the penalty that player J would pay if the constraint is not satisfied? Of course, if at any node NT, the constraint is satisfied without equality, is not binding, the corresponding multiplier will be equal to 0. So now we can do this, and yes.
Excuse me, George.
Yes, Hassan.
So when you introduced the R's, you mentioned that a regulator could be coming up with these R's in the game. But here in this setup, who is coming up with the R's?
I will discuss it a little bit later on. This is the manufacturer who is selling to different retailers. So you may say that retailer A is a very good one. I have been in a relationship for the last 10 years. I will give him a different weight from other one. Of course, here we are going to solve for equal weights. But
so here it's the manufacturers. Okay.
Yes, because it affects the flow that is going from the manufacturer depots to each one of the retailers.
Okay, thank you.
Okay, so here you can state a maximum principle for this equilibrium. Essentially, it's like before, given that you have Q prime satisfying the conditions for a Nash equilibrium, you can find there exist multipliers satisfying the conditions of optimality, co-state equations, and complementarity conditions. Okay. Now, to illustrate all this, let me give myself the simplest possible setup. So we have two retailers, and we have four decision stages. So this set is from 0 to 4, but recall that at the last stage, we don't have decisions. And suppose that the stochastic parameter, which is the total available supply at the manufacturer depot at NT, so it can take two values at any node. It can be either equal to 0 with low probability, or it can be at its upper value, 4, with probability 0.9. Now, to solve for the problem, I need to give myself a functional form for the salvage value. So we are assuming that the salvage value is quadratic, and the parameters theta and kappa are chosen in a way that they are that this function is concave increasing. Okay, now what we have here in any DGPET is that you have scenarios. So here in this case, because we have binary tree, we will end up with 8 scenarios. So for instance, along the scenario that it's emanating from initial node to this one particular node, you have 0 disruption, and the probability of this scenario is 0.72, and so on and so forth. Okay. Why I'm highlighting this? Because, for instance, after that, if you want to compare what is happening along this particular scenario with something else, you have to be careful, because each scenario can be compared to its own scenario, but when you vary maybe some parameter values. If I'm not mistaken here, square nodes mean that we have shortage, meaning that Sn is equal to S lower bar equal to 0, and the circle, it means that the capacity is at its upper value. And as I said, we end up with a binary tree like this one with n terminal nodes. So now once we have this, we can write the equilibrium conditions first for the case where we are jointly optimizing, and second for the case where we are decentralizing it to normalized Nash equilibrium. So I have to go fast here for lack of time. So everything must be done numerically. So we give ourselves some parameter values. So what you can find in the paper is a lot of details regarding the results. Essentially, we are considering 4 cases that we suppose that are of interest. The first one is a symmetric case, meaning the 2 players are facing exactly the same parameter values. And after that, we look at a case where the holding costs are different. Second one, the salvage values are different. And the last one is the case where the initial inventory is not the same. I will present the results in a very qualitative way. First of all, the expected payoff that we obtain under the unconstrained Nash equilibrium are, of course, higher than in the case where we have normalized Nash equilibrium. And this is in all cases. By adding this coupling constraint, players cannot improve their fate. And this is true even when you have zero probability of disruption. And the ratio of players' profit is almost the same as the ratio of their weights. So when you compare the profit of a player under non-constrained Nash equilibrium and normalized Nash equilibrium, they follow very closely the ratio of their weights. Of course, the profits that the players are collecting along the different scenarios are very different from one scenario to another. In terms of inventories, what we observe is that when we consider the symmetric case under the unconstrained Nash equilibrium, no inventories are made in early periods, whereas in the normalized equilibrium, players are building their inventories from the outset. Why? Because there is this coupling constraints. The result in the asymmetric cases are relatively straightforward in the sense that if you give an advantage to a player, the profit is higher, and the inventory paths are highly affected by the varied parameters. So this is interesting to study in some empirical cases, I guess. And the advantage player is ordering more than the competitor. So what are the conclusions that we can draw here? I believe sincerely that this framework is interesting to deal with competition among few firms when we have uncertainties. Conceptually, an event tree is really mimicking how decision makers are thinking about uncertainty. For instance, if you look at the price of oil next year, what decision makers will be considering are few values. They are not considering tons of values of how much the price of oil could be. So a tree is mimicking this process. Computations are relatively easy. And of course, with a framework like this one, where everything is done numerically, you can do as much as you want sensitivity analysis to assess the impact of this or that on the results. Now, in terms of extensions, here we are assuming that the shortage can last for one period. You can, of course, assume something else. And now, what would happen if the players, instead of thinking in terms of what we have done, implementing S-adapted open loop strategies in the usual sense, what would happen if the players are implementing some robust strategies, thinking in terms of worst case scenario? So here there is some work going on with Elena Parilina and Ping Son regarding first developing the theory of dynamic games played over event trees under the assumption that the players are using robust strategies, and also to look at different possibilities in terms of defining robustness, worst case, regret, etc. Here we assume that all players have the same beliefs about how the tree is, how the stochastic process is progressing. For instance, here all players are believing that the probability of going from node N0 to N11 is 0.9. In fact, you don't need to do it. You can assume that the players have different beliefs. And this is a case that has been also recently studied with Elena Parilina. In the case of cooperative dynamic games played over event trees, it has not been yet done for non-cooperative games, but I guess it is feasible. And I will finish with an advertisement spot. Everything you want to know on this class of game, games played over event trees, non-cooperative and cooperative. is this book published with my two good friends, Vishwa Reddy and Elena Parilina, is by Springer. If your library is connected to Springer, you can download the book for free. And if you have difficulties in downloading the book for free, I think the three authors are nice enough to send you a copy. Thank you very much for listening, and I'll stop here. I left 5 minutes for